Welcome to Pre-Calculus. Today we will investigate graphing sine and cosine functions where I've got some kind of amplitude or period change. We'll take a look at three total functions to graph. Our first function is y equals 4 sine of theta. So our instructions say to graph the function by creating a table of values for a complete cycle. And then we want to identify the amplitude and the period in radians. So again, let's start by creating our table of values for this function. We practiced graphing the basic trigonometric functions. So what's different here is going to be this 4 that's multiplying times the sine of theta. So we'll look for that change in the output. For the input or our domain values, what I want to do is create really one full cycle. So I know for sine, it's going to be from 0 to 2 pi. So what I'll do is that's what I'm going to include in my table. And then what we'll do for the other negative values is we'll just kind of recursively use our pattern to find that left side of the graph. So we'll start with 0, pi over 4, pi over 2, 3 pi over 4, pi, and then 5 pi over 4, 3 pi over 2. And make sure I fit all that in there. 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. So we'll start with 0 here. So to help me calculate these values, I again want to bring the unit circle like we did on our last graphing where we were graphing the basic ones. So essentially I want to take unit circle, and again, just to remind, for sine, those are my y coordinates, the ones that are highlighted in green. But I do need to multiply each one of these by 4. So for the first one, I'm looking for 4 times the sine of 0. Well, sine of 0 is going to be that green 0. So it's 4 times 0, which is just 0. Moving to pi over 4, that's going to be 4 times square root of 2 over 2. So recall square root of 2 was 1.41. So it has the value of about, when I divide it by 2, of about 0.7. So if I'm multiplying 4 times 0.7, that's going to give me 2.8. Now at pi over 2, 4 times, so my value at pi over 2 was 1. So that's going to be 4. And as we move to 3 pi over 4, what we're going to see is a repeat now. So now I'm going to get 4 times square root of 2 over 2. So again, square root of 2 over 2 is about 0.7. 4 times 0.7 is 2.8. And then when I reach pi, pi again has the value of 0 as its y coordinate. So 4 times 0 is 0. Now, I'm going to get the calculation for the next value, and then I want to see if I have a pattern that I can use to speed up the table making. So here at 5 pi over 4, that's got the y coordinate negative square root of 2 over 2. So it's all the same, except this is negative. So that's going to be equivalent to 3 pi over 4 is 2.8. It's just going to be negative 2.8. And then I can use my pattern. Next one should be negative 4. See how that mirrors the 4? Negative 2.8, 0. So what we'll do to graph this is we're going to just go to our plane. We'll graph our points we've got. So that's 0 at the origin. And then picking up pi over 4 is now 2.8. Pi over 2 is 4. 3 pi over 4 is 2.8. Pi is 0. 5 pi over 4 negative 2.8. So already we can see that this has the same patterning as the sine function. It's just taller. So the right side of this function is going to look very similar to our sine graph. It's just got a very much changed amplitude. Now I can use this pattern to graph the left side of the graph as well. So as I go to negative pi over 4, that's going to clearly be at negative 2.8. And I can continue. Negative pi over 2 is negative 4, negative 2.8, 0, 2.8, 4, 2.8, 0. And that quickly sketches in the left side of our graph. So what we're seeing with this initial example with a change, when I've got a multiplier out front, essentially what that's going to do is it's going to dilate our period. I'm sorry, dilate our amplitude. I said the wrong one. So one thing that we can see is that that number, that 4, should match our periods or our amplitude. So as I look here at this first wave, it definitely has a height of 4 above the x-axis. So our amplitude equals 4. And what we'll start to see is that this value, if I think about the function generally as f at theta equals a, in this case, sine of theta, that a is one of the parameters that will change our amplitude. And in fact, amplitude is going to equal the absolute value of a. So we've actually calculated it here for this example, but what we can start to do is predict based on an equation. Well, let's take a look at a second example. So that first example changed the amplitude. Before we go, we should say what the period is. So period, again, it's a full cycle. We've kind of noticed it here. So our full cycle is from 0 to 2 pi. Our period has not changed. So that a multiplier out front does not change the period. Well, let's look at one where the period does change. So here we're looking, second example is y equals sine of 3 pi. So as I create my table here, I need to think about where that 3 is multiplying. It's multiplying onto the theta value. So as I think about how that's going to change the graph, when that multiplier was out in front of sine, it changed the amplitude or the height of the wave. If it's on the inside, multiplying times theta itself, so see how that 3 is on the inside of the sine function, what we might predict is that it's going to change not the height, but the width, which is equivalent to our period. So what I want to think is, how exactly is it going to change the period? Well, let's just pick up a few of our values. So I'm going to take, essentially, I want to take the period, which is from 0 to 2 pi, and I want to divide that by 3. And essentially what that's going to give me is it's going to give me my new period. So I need to really take 2 pi over 3. So if we kind of locate where that is with relation to pi, 2 pi in fact, I'll put pi there in our table, so that's halfway between 0 and 2 pi. But then what I want to do is I want to partition 0 to pi into thirds. So I'm going to put pi over 3, 2 pi over 3. And I just want to see how that's going to adjust my output. So I'm not going to create my whole table at first for this example, since we're just investigating here. So I'm going to pick up, let's calculate the output. So it is based on this function, sine of 3 theta. So we'll start with 0. So sine of 3 times 0 is going to be sine of 0, which we know from unit circle. So let me get the unit circle again. So we'll come back to our graph. We got to create our table first. Is going to actually be, so if I'm here on the unit circle, sine is the y value, so sine at 0 is 0. So that doesn't change. But let's pick up with pi over 3. So this is going to be sine of 3 times pi over 3. So when I multiply that out, my 3's are going to cancel, and that's just sine of pi. So sine of pi is also 0. And so what we're seeing is that this function has, because it's been multiplied by 3, it's been compressed horizontally. So we'll check in a minute if we can catch the extremes. But let's see, I think 2 pi over 3 should also have the value of 0. So let's plug it in, sine of 3 times 2 pi over 3. So again, my 3's will cancel, and that's sine of 2 pi. And that is back around at the beginning, back at the standard position. That also equals 0. So what I need to catch is what's in between these. My outputs are all 0 now. So I'm going to catch the pi over 6, the 30-degree increment. So I'll put pi over 6. I'm also going to put, if we catch between these, so if I add pi over 3 plus pi over 6, that's back to 90, so pi over 4. So let's calculate for those, and then we'll extend the pattern for the rest of the function. So sine of 3 times pi over 6. The 3 is going to cancel, leave a 2 in the denominator, so that's sine of pi over 2. And when I look at pi over 2, that's the positive y-axis. That is a value of 1. So I want to confirm this pattern. I think sine at pi over 4 is going to be -1. So let's see if that's in fact the case. So I'm putting it in the function. Sine of 3 times pi over 4 is sine of 3 pi over 4. And when I go to 3 pi over 4, that is right here. I put the wrong measurement there. And that's kind of the case with a lot of these radians because it's fractional. I don't want pi over 4, I want pi over 2. So I'm just going to make that correction across my table here. And what that's going to place me at in terms of my degree or my angle measure is 3 pi over 2. And that's better because that's where I'm looking. So that's down here in the negative y-axis. And that does confirm the pattern. That's -1. So I've got kind of an incomplete table, but it gives me one full cycle of this sine of 3 theta. So what I'm going to do is I'm going to graph that one cycle. So what I had done was I had taken pi over 2 and split this into thirds. So I've got to reorganize my x-axis. And notice that splitting into thirds really mirrors that multiplier. So again, what we started by doing was dividing our normal period by 3. We took 2 pi and divided it by 3. And it's showing up here on our graph. So the way that I see this function graph now is at the origin, so 0, 0. And then at pi over 6, so that's my first third there, I'm going to have the value of 1. Pi over 3 is back to 0. Pi over 2 is -1. So then what I see is over 2 increments, I have to split it into thirds. So I'll make that partitioning here on the x-axis again, and let's complete the pattern. So at 2 pi over 3, we're back to 0. That's one full period. So kind of our first view, if I multiply the theta by a whole number, it's going to actually compress the graph side to side. Now I can continue that pattern as I go. So my next value as I go is going to be at 1 back to 0. And then we can just continue that pattern. So I'll mark a third here. In fact, it's 2/3 of 1 unit. And that's going to take me back down to -1. Okay, we'll do the same in the negative now that I see the pattern. So you take 2 of these and you want to divide it into 3. And we'll keep going negative direction as well. And then let's just continue our pattern. So we were at +1 at pi/6, 0 at 0. So downward at -1, 0, 1, 0, -1, 0, 1, and so forth. And we'll just place our curve. And that completes that graph. So notice when I create my table here, I'm not after every single point. What I'm after is outputs for one full cycle. So to kind of summarize what we did, when we have a multiplier, what we'll do is we'll call this a b value. So we'll say we got f at theta equals sine of b theta. To find my period, I want to take the normal period of sine, which is 2 pi, and divide it by the b value. So what we saw here was that gave me the value of 2 pi over 3. And essentially, if I mark 2 pi over 3 here on my graph, that's now 1 full period. So we can mark that here. The period equals 2 pi over 3. The last thing we want to check again for the analysis is what's the amplitude. Well, this one did not have an a multiplier out front. Remember from our previous example that had a 3 out front. We have no number recorded there, so it's just going to be its standard 1. And we can see that on the graph. The height of each wave is 1. Let's take a look at a third and last example where we have both changes. So on this example, we have y equals half times cosine pi over 2. So what we can do here is start with our table, and we'll put our full, well, in fact, what we'll do is let's start with 0. And what I want to do is see, based on our rules, how we should predict our period. So here, like I can think of this one, it's really half times cosine of half theta, just to separate that multiplier off of the angle measure. So I know cosine has a period of 2 pi. So my period for this transformed function is going to be 2 pi divided by that value half. Well, when I divide a number by a fraction below 1, it's like multiplying times its reciprocal. So that's 2 pi times 2, which is 4 pi. So in fact, what I got to do for this cosine function is go out to 4 pi. Well, I can't go out to 4 pi. My graph only goes out to like 3 pi, unless I extend it. So I will extend it to 4 pi there. So that's what I should expect for my full period. So I'm going to include 2 pi, and then I also want to include pi and 3 pi. And one thing you can do to help with just the domain is look at the x-axis. It's scaled to really match what we've got here. Well, let's calculate the output. So I'm going to put the function, it's half cosine theta divided by 2. And we'll take a look at our trusty unit circle. And up till now, we've been trying to graph sine functions. So we've been going to those green values, the y coordinates. Where we want to go for cosine are the yellow x coordinates. So we'll do that. I'm going to pick up here at 0. So I'm just going to plug it in first. So it's half times cosine of 0 divided by 2. So that's cosine of 0. So I'm looking at the x value of the standard position. That's my cosine value. So that's half times 1, which is 0.5. Okay, so now we'll move to pi. So again, I'm going to just plug it in my function, half times cosine of pi divided by 2. So cosine of pi over 2, if I go to that positive y-axis, the cosine value there is 0. So it's half times 0, which is 0. Okay, now 2 pi. Half times cosine 2 pi over 2. My 2's are going to cancel there. So it's really cosine at pi, and that's -1. So that's half times -1, which is -0.5. So I'm starting to see a pattern in my numbers. I went from half to 0 to -0.5. My prediction for 3 pi is that also should be 0. But I'll confirm it. So it's half cosine 3 pi divided by 2. So I'll go to 3 pi over 2. The x value there is 0. So it's half times 0, which is 0. And that confirms my pattern. So I think 4 pi should be back at half. So we'll confirm by calculating half cosine 4 pi divided by 2. 4 pi divided by 2 is going to be just 2 pi. So that's back at the standard position. That's a value of 1. So that's half times 1.5. So let's graph what we've got. Again, I don't need to create a table for the whole domain. I just want one full period, and then I can extend based on the patterning. So here at the origin, and then at pi, actually, I marked that incorrectly. At the value of 0, it's at half. So cosine's a little different than sine. Pi is at 0. 2 pi is at -half. 3 pi is at 0. 4 pi is at half. So what I see when I connect this curve is that it's a very flat, stretched out function. It's been compressed vertically, stretched horizontally. And I can continue this pattern for the negative values. So to the right, it went 0, I'm sorry, 1, half, 0, -half. So if I back up, it's going to be half, 0, -half, 0, and then extending it to -4 pi half. And that completes my graph for this vertically compressed, horizontally stretched graph. So let's see if we see those things with the stretching and the compression. So for my period, I had that it should be 4 pi from the algebraic calculation, and I see it here on the graph. It takes a full 4 pi to complete one full cycle of cosine. So I'm going to mark here period equals 4 pi. And just to kind of confirm that, reiterate where we got it algebraically, you take your usual period for cosine, that's 2 pi, and divide it by that multiplier b. And that's where we got 2 pi divided by half is 4 pi. Last thing for us to notice is the height of each wave. Remember, we called that amplitude. So I can see on my graph that the amplitude is equal to half. And that matches what we were noticing with the multiplier out front. That's my a value of half. So that matches what I'm seeing on the graph. The height of each wave is not the full one. It's compressed to a half. Thanks for joining for this investigation of graphing sine and cosine functions where amplitude and period have changed. See you soon.